Hello, I'm Roman, and welcome back to a series of the videos Neural Networks from Scratch in Golang, where we're using a book called Neural Networks from Scratch in Python, but we're writing everything with a Golang. And in the previous video, I finished with what it was called model evaluation. So right now we have actually a method. If we'll run it, we can evaluate a model against a concrete data set. We're using this during the training. So once the training is finished, we evaluating, and the main thing is to actually just print the validation loss and validation accuracy. And yeah, we can do the same for against any type of the data. For example, here I have the validation data, here I have the against the training data. By the way, why it's training data, it's with the small one. That's better. Okay. And yeah, and for example, in the future, we could have training data, validation data, and testing data from the same data set, and we can test the model against fully unseen data. What we're going to do today, we're going to the next chapter, and as I checked before, there's actually not much left in this book for us to cover, but see, I think I will spend some time on the inference, at least this is my plan, on the prediction inference, and create some, for example, backend microservice so we can use the model that we could train with this tool. Yeah, and maybe even try to Dockerize it and run it on some, Linux machine, etc., but that will be in the future episodes. Today, saving and loading models and their parameters. And this one could be an interesting, I'm not sure. Well, I mean, probably it will be very different from what we have for the Python, because the way how we will store and load the data between the Python magic and what we have with the Go probably will be very, very different. So let's see, where is it? Sorry. Okay. There are situations where we would like to take a closer look into the model parameters to see if we have dead or exploited neurons. To retrieve these parameters, we will iterate over the trainable layers, take their parameters and put them into a list. The only trainable layer type that we have here is the dense layer. Let's add the methods to the dense layer class to retrieve the parameters. Okay. Get parameters, and within the model, I think the parameters list parameters append get parameters, and what it will do, okay, create the list, and then instantiate, print parameters. Okay, so that will be array of arrays, right? Oh, interesting. Okay, let's do one by one. So get parameters for the dense layer. I'm not sure if I have the LSP running. Okay, so we have the layer, this one, right? And what do we do? We want to edit only for the layer, so it doesn't make any sense to edit for the interface, right? And what we want to take, the weights and biases, right? And then there is a question how I want to return it, because the main dance is, well, there is a plus 64 general, but also there is a cap row and the cap calls, which returns the two-dimensional size. And I'm thinking, do I want to return like elements itself, or just By the way, how the weights is actually where is it? Number of the neurons. Okay, so it's a two-dimensional. Okay. I mean, I'm not sure why I need to do this. I have the weights and biases exposed already, so I'm not sure why I need to do this. Okay, let me dive into this and understand what actually the result. So we have so that returns a tuple, right? The tuple of two arrays, well, numpy arrays. And that's actually will hold. Okay, array. This will look something like within the. Okay. Setting. If we have a method to get the parameters, we'll likely also want to have a method that will set the parameters. We'll do this similar to how we set up get parameters method, starting with the. Okay. Imagining that we do this, but I have the initialization, right? And the main thing of the initialization is to actually create the new one. But if we'll have some sort of the what's called serializing, deserializing, I can access it directly, right? Okay, then we can update the model. Okay, let me study this part and then think how we can use it, implement it in our way. We're also iterating over the trainable layers here, but we are doing next needs a bit more explanation. First, the zip function takes the iterable like list and returns a new iterable with pairwise combination of all iterables. Yeah, so it's basically kind of returns the parameter set from the parameters and the layer from trainable parameters from the same index. So we kind of have the tuple. If one of them is bigger, so zip takes the shortest length. For example, if it's 5 and it's 10, we'll have 5 iterations. This approach gives us flexibility if we would like to use layers with different numbers of parameter groups. Okay. One difference that presents itself now is that this allows us to have a model that never needs an optimizer. If we don't train a model but instead load already trained parameters into, we won't optimize anything. To account for this, we'll visit the finalize method of the model class, changing to if loss is not none. So basically, next we'll change models class setter to allow us to pass in only given parameters. We'll assign default values and if statement to use parameters only if they present. To do that, we'll change. Okay, so basically the idea that we could have an empty loss optimizer and accuracy, right? Retrieve model parameters, instantiate a new model, set parameters, evaluate. Okay, so okay, probably I will study this chapter today to see, well, study this chapter and take a look at the ways we can serialize objects in Go, because maybe we have something default. Because, for example, what I mean, for example, the layer is the struct, right? If we take a look, the dense is a struct too. If we go next, last 64 general is a struct which contains from the simple. So if there is a way to, like, for example, I remember in the C# in the .NET, it had the default serializer that you can pass some class hierarchy of the objects, and you call the serializer and you pass the type of the serializer like XML or JSON serializer, and it will serialize all of the data inside it, and you can retrieve the data same way. I didn't have to write this serialization by myself, so I will try to find the same in the Golang. I mean, I think it should be like this, right? So, for example, then I can, for example, if we take a look at the model, we'll have all of the things serialized, and that's it. Because accuracy, serializable, it's a struct under the hood, optimizer, loss, all of the things uses objects, uses structs implemented in the specific interface. So let's see, but I will study the book first. Well, at some point. We'll extend this further by actually saving the parameters into the file. To do this, we'll add the save parameters. And then we'll use Python's built-in pickle model to serialize any Python object. Serialization is the process of turning an object, which can be of any abstract form, into binary representation, a set of bytes that can be, for example, saved into the file. This serialized form contains all the information needed to recreate the object later. Pickle can either return the bytes of serialized object or save them directly to the file. We'll make use of later ability, so let's... Okay. We'll add a new method to model class. Before having pickle save our parameters into the file, we'll need to create a file handler by opening in binary write mode. We'll then pass this handle along to the data into the pickle dump. Okay, basically it's a way to dump. But it stores only the parameters, right? It's okay, loading of the parameters, load parameters. Okay, so we kind of pickle load, and in that way we sort and retrieve the params. Okay, this one, right? But we need to understand the model architecture, right? How many layers, what are the activation functions, etc. Saving the model. Okay, saving the model, this one, right? And loading the model. Okay, so I will check the whole book here, and probably that will be the video about the exploration of what else I can do later. Why did we save the whole model in the first place? Saving just weights versus saving the whole model has different use cases along with the pros and cons. With save weights, you can, for example, initialize the model those weights, train from a similar data, and then train that model to work with your specific data. This is called transform learning and is outside of the scope of this book. Weights can be used to visualize the model, like in some animations that we created for the purpose of this book, starting from chapter 6. Identify that neurons implement more complicated models, like reinforcement learning, where weights collected from multiple models are committed to a single neuron, and so on. File containing just weights is also much smaller than the entire model. Okay. Model initialized from the weights loads faster and use less memory, as the optimizer and related parts are not created. That's true, but it's not the biggest part. No, the biggest part is the parameters. On the outside of the loading just weights and bytes, it is that the initialized model doesn't contain the optimizer state. But okay, so the idea, okay, you can load, for example, here, you can load all of these parameters only if you'll recreate the same model architecture. Then, for example, it will go like it take the first params into the layer dense, then this one and then this one. It is possible to train the model further, but it's more optimal to load a full model if we intend to train it. When saving the full model, everything related to it is saved as well. This includes the optimizer state that allows us to easily continue the training and the model's structure. We'll create another method in the model class that we'll use to save the entire model. The first thing we'll do is to make a copy of the model, since we're going to edit it before saving, and we may also want to save the model during the training process as a checkpoint. Deep copy. Oh, that's actually will be interesting to how I would do this in Go. The copy model offers two methods that allow us to copy the model: copy and deep copy. While copy is the faster, it only copies the first level of the object's properties, causing to have some common references to the original model. And I could have the same, but I will need to implement that manual, because, for example, let's take this one. GI, yes. So I have a bunch of the implementation. For example, if I will take a look at the layer, there are some things. Maybe I should just, I think that could, I remove the reference to it. This is the same. Yeah, that's actually interesting how we do that. For example, our model has a list of the layers. The list is the top level property and the layers themselves are secondary. Therefore, reference to the layer object will be shared by both the. So we need to do a deep copy. Next, we'll remove the accumulated loss accuracy. Well, okay, from the copy. Then remove any data in the input layer and reset the gradients if any exist. Very nice. Okay. Input layer, take it as a dictionary and remove the output. Okay. And the inputs. Okay. Both model input layers and the model loss are class instances. They are attributes of the model object, but also objects themselves. Done because of the double underscore that exists for all classes is a dict property. It contains names of the, yeah, this is the pure Python magic. Next, we'll iterate over all the layers to remove their properties. With this thing clean up, we can save the model object. To do this, we have to open a file and again in the pickle. This makes the full methods. Okay. And that will be our model. Then loading. And there is a static return model. I really don't need to read this. Okay, that returns the model. Saving the full train model is a common way of saving the models. It saves the parameters and the instances of all models object and the data they generated. That is going to be, for example, the optimizer state like cache, learning rate, decay, full model structure, etc. Loading the model in this case is as easy as calling one method and the model is ready to use whatever we want to continue training or to use it for prediction. And this is okay. Okay, this is the okay, let's start from the first. I'm not going to implement this for now. I want to create saving and loading of the whole model, but the implementation wise it will be very different in the Go because of the differences in the languages. So okay, so what do? Do I have the I will do a small investigation and I will start the implementation probably in the next one. Do I have the serialization? No. Saving. Okay, more encoding JSON XML. Okay, the JSON encoding of V. Marshal traverse the value very recursively. If encoded value implements Marshal and is not a nil pointer, Marshal calls producer JSON. If no method is presented but the value implements encoding text Marshal instead, Marshal. Okay. Array and slice values encode as JSON array except by encodes by 64 encoding string. Oh, okay. And I need to turn Marshal JSON into interactive value and Marshal. But do I have the binary one? Okay. Let's Google. Golang store serialize structs to binary. Okay. Serialize. We have generic and fast binary serialize of Go. This represents decode arbitrary Golang data structure of various size, zero location encoding, support for maps, arrays, slices, and structs, primitive and nested types. This is essentially a JSON Marshal drop-in replacement. I want this package to be simple to use and leverage the power of reflect package. The ints and uints are encoded using varint, making the payload small as possible. Okay, so I actually can start from... So most likely, because of the values that it supports, to Marshal stores one of these bool, float 64, string, array of inference, JSON objects. Okay, let's take a look at the example. So we have, okay, and Marshal into this one. Okay, what I've been thinking so far. So probably I will need to either implement the encoding text Marshal or all of the things, or for example for this one, so it can be used, or I will have to do a copy, or I mean, I will have to do a representation of the model using the, what's called, only simple, like built-in data. Like for example, instead of the, so for example here, instead of every place where the mat dance is used, because I'm not sure if it's possible to store it in, in this form. So probably I will have to do a copy of the model into a different representation that can be serialized with this, and then I will load it from the JSON or any other type of but probably we'll start from the JSON just to have the visual, like to have the visibility on what is stored, so I can actually check that I did it correctly. And then I will instantiate the model from this like proxy data and this. Probably that will be the way I will implement it. I will stop recording for today. I will search a little bit more about this if I, if there is a way to serialize the MatDance class, well, struct, so I don't have to do this proxy data. If not, I will implement it in the next video. If yes, I will implement it in the next video, but it will be just more faster implementation. But basically what the next goal will be to implement the saving of the model. I'm not going to save the parameters for now. Saving of the model, loading of the model, and then I can use it to do the inference. Yeah, that's the plan for the next video. Okay, thank you for watching and see you in the next video. Bye bye.